Hi everyone, so today we're going to start this lesson off with just a little bit of review of the anatomy of the respiratory system. So here we have Frank, and I'm better at drawing cartoons than I am real people, so he will be our model today. So the only external portion of the respiratory system is the nose, and we specifically inhale air through our nares, or also known as our nostrils. And then once the air, we'll use this blue to represent our air. So our air goes in through our nostrils, and it goes into the nasal cavity, which we'll just kind of circle this spot as the And then remember, in our nasal cavity, we also have some sinuses that allows us to have a more hollow skull, and they're also responsible for creating some sound. Because remember, when Miss Gerald plugged our nose, she kind of sounded nasally. And when the sinuses allow a little bit of air passage to get through there so that we can talk with our full force. So moving down the respiratory tract, the air continues to move until we hit the pharynx. And the pharynx is just kind of like in the back of the throat, but even in the back of the throat, and we have three types of pharynxes. We have the naso, which resides just behind the nasal cavity. We have the oropharynx, which resides closer to the oral cavity. And then we have the laryngeal, or as my British professor called it, the laryngopharynx, right below the oropharynx, and that's closer to the larynx, which is more closer to the start of the lungs. And then just inferior to the larynx, we have the trachea. Now this image is not drawn to scale, and you can feel your trachea when you palpate your neck. And we also refer to our larynx as the throat in layman's term. And then once we're at the trachea, it branches off into the main bronchi. And then we have our lungs, which I'll draw half, kind of like that. Remember, our left lung has two lobes because the heart resides more towards the left side of our body, while our right lung has three lobes and is just a little bit bigger, and so is the bronchi. So you have more of a chance of getting something caught or debris in the right bronchi than the left, just because of how the passageway is connected to everything. Now I forgot one little tiny structure that prevents debris from coming in, And I'm just going to draw the esophagus right here. And we all know that the esophagus is the passageway that leads to the stomach to continue digestion. But we have what's called the epiglottis. And that prevents any food going down into the larynx and into the trachea, and make sure that only food goes down the esophagus. So after we branch from the main branch, we have the secondary and tertiary and maybe quaternary bronchi, which lead to the thin bronchioles, and then which eventually branch off into these grape-like structures called the alveoli. And the alveoli also have these capillaries wrapped around them, almost like spider webs. And that is to ensure oxygen and blood exchange, which leads into the 4 stages of respiration with external respiration. And that's where the meat and potatoes of today's lesson is going to be about, is the 4 events or phases of respiration. Okay, so to kick off the 4 stages of respiration, I have posted a Word document with supplemental text from, I believe, your big anatomy book. And that goes into just a little bit more detail about the mechanics of breathing and respiration in general. So the first stage of respiration is pulmonary ventilation. And pulmonary ventilation is just the mechanical and physical manifestation of breathing. So that is when we notice someone taking a deep breath in, they are experiencing pulmonary ventilation. You can probably equate it to almost like as an oxygen uptake. And this is the kickoff of respiration. So when we inspire during pulmonary ventilation, there are a couple of different pressures that we need to be aware of. And since we are dealing with a gas, air or oxygen, we need to understand some basic gas laws so that we can really understand what is happening within the lung. So I'm going to begin with what's called atmospheric pressure. And sometimes it's abbreviated as ATM. And when it deals with anatomical pressures, our units that we use are millimeters of mercury. And 1 ATM equals about 760 millimeters of mercury. That shouldn't be there. So 1 ATM. And when we talk about the other types of pressures within the lung, we're always speaking relative to atmospheric pressure, because that is the pressure that is exerted on our bodies in the natural environment. And so the first pressure we are going to talk about inside the lung is the intrapulmonary pressure. And sometimes it is abbreviated to P subscript pul. And this is the pressure within the alveoli. And something to know about intrapulmonary pressure, it will eventually equalize to atmospheric pressure. So when we inspire, we reach a certain threshold, and that threshold is atmospheric pressure. And once it does that, we are able to begin the second phase of pulmonary ventilation, which is expiration. The next pressure that we should be aware of before we move on to the finer details of respiration is the intrapleural pressure. And the intrapleural pressure is always going to be negative. And it's always negative to ensure that the lungs do not collapse. And the pressure during the breathing phases fluctuates, and it can fluctuate because it will always have that negative pressure. It has more leeway to increase or decrease, so it doesn't reach atmospheric pressure. And intrapleural pressure is abbreviated as P subscript IP, or I like to call it the PIP pressure. And the negative intrapleural pressure is established by two things: by the lungs' natural elasticity, and then also the surface tension of the alveolar fluid. And there's surface tension because the fluid lining of the alveoli attract to each other, and that's what produces the surface tension to make the alveoli as small as possible. Okay, so moving on into one more gas law before we continue with pulmonary ventilation is Boyle's law. And Boyle's law states the inverse relationship between pressure and volume, and the following formula is P1 times V1 is equal to P2 times the volume of the second container. And the inverse relationship comes from this multiplication right here. So if we have a decrease in pressure, we are going to have an increase in volume. And that relationship will be reflected on the other side of the equation. And so if we think about what we know about gases, gases always fill the entirety of their container. Because they have this more fluid nature to them, when they fill the entire container, for example, we have a container here and we fill it with gases. When there is more volume for the molecules to move around in, there's going to be less pressure because they're not going to be forced into each other. Whereas if we have a smaller container and we put the same amount of molecules in there, the pressure is going to increase because the molecules are going to be acting upon each other more. There's going to be more collision or more chances of collision. So that is why when the volume decreases, the pressure increases, and vice versa. When the volume increases, the pressure is going to decrease because the gas molecules are not going to be acting upon each other. So after that quick trip down physics memory lane, let's get back into the nitty-gritty of chapter 13. So, under pulmonary ventilation, we have two phases: inspiration and then expiration, which I will wait to write after. So during inspiration, the diaphragm and the intercostal muscles are going to move. And the diaphragm is this kind of semicircle shape with these two larger lobes at the end. And the diaphragm just resides underneath the lungs and the thoracic cavity. And so when it contracts, it's going to move inferiorly or down as it flattens out. And so this causes the thoracic cavity, its height, to increase. And you may say that's a little backwards, but it makes sense for when we take a deep breath in during pulmonary ventilation. We need our volume of our lungs to increase to take on that tidal volume of 500 milliliters of air, so we can increase our lungs and make room for the air that will be coming in. And secondly, the second muscles that help are the intercostal muscles. And the intercostal muscles reside within between your ribs, kind of like this. And the intercostal muscles help move the ribs up to make room for your increasing volume within your lungs. They're able to move semilaterally to expand just a little bit. It's pretty not noticeable, so that we can take on this air. And it moves all together with that thoracic cavity because of the pleural fluid. That super sticky adhesion allows the entirety of the thoracic cavity to move all together. So after inspiration during pulmonary ventilation, you're going to have to experience expiration as the second event. And expiration for a healthy person is passive. And it's passive due to the elasticity of the lungs and that helps with the muscle contraction of the diaphragm and the intercostal muscles. And so as the volume decreases, the pressure is going to rise because our lungs are relaxing. They're going into their natural resting state. And so the intrapulmonary pressure is going to rise slightly above atmospheric pressure by approximately 1 millimeter of mercury. And when we have that slight increase, we're able to get this concentration gradient where the concentration of air is higher within the lungs, and it naturally wants to move to a lower concentration. Think about after you go for a really long run, you're tired, and you want to bring your body to a complete rest, so it feels good to naturally sit down and take a load off after you ran a long time. This is kind of what is happening in air. Air has built up and wants to move to a lower concentration, and that's where you get the exchange of air moving from the lungs out of the lungs to be passed throughout the whole entire body. So after we complete pulmonary respiration, the next phase of respiration is external respiration. And during external respiration, we are able to experience the changes of the blood color to become oxygenated from deoxygenated. So the main piece of evidence is that deoxygenated blood is this dark red, doesn't look as pretty. And when it is deoxygenated, there is a lack of oxygen molecules, and so it needs to become reoxygenated into the bright scarlet red blood that we typically think of. So it goes from deoxygenated to oxygenated. And that happens by 3 events or 3 phenomena. And those are the partial pressures and solubilities Next, we have this matching, or also known as coupling, of alveolar ventilation and pulmonary blood perfusion. And I'm just going to call that the ventilation perfusion coupling. And I'm going to talk briefly about that because that can be a little confusing to understand. And next we just have the natural structure of the respiratory membranes. And the membranes allow for that gas exchange to happen on a tissue level. So partial pressures can be identified by using Henry's law. And Henry's law states that the percent of the partial pressure times atmospheric pressure in millimeters of mercury gives you the partial pressure in millimeters of mercury. And Henry's law is important because air is not 100% O2. And we have other mixes of gases in there. We have a little bit of CO2, maybe a little nitrogen. However, oxygen does make up the majority of air, but we have these other two gases present. So this is where the first phase of external respiration becomes important, and that is Henry's law. So next we're going to talk about the second phenomena that happens during external respiration, and that is the ventilation-perfusion coupling. And ventilation is also known as the gas reaching the alveoli. Where perfusion means the blood is reaching the pulmonary capillaries. And these two work together to create this gas-blood gradient. And to allow this gradient to happen, blood and gas, or in this case air, have to work together to ensure that the body becomes oxygenated via blood. And in the text, the supplemental text on page 829, there is this great diagram that explains how the ventilation perfusion coupling works together. And just a reminder, external respiration deals with the outside environment, so that is us bringing air into our bodies to oxygenate the rest of our blood. And then finally, we have the last stage, which is internal respiration. And internal respiration is the gas exchange to the tissues.